Okay, so today we're going to be talking about heating, ventilation, and air conditioning equipment, also HVAC. So it's important that we have pronunciations of all the acronyms that we develop in this class, DERS and HVAC and so forth. So we'll talk about electric resistance heating. We'll talk about heat pumps. So who has not heard the term heat pump before, at least outside of this class? Okay, who has heard of a heat pump? Yeah, I mean, you guys are Purdue grad students and we're the Boilermakers, so we're all nerds for heating and cooling. So it doesn't surprise me that you've heard those terms. We'll talk about heat pumps, we'll talk about air conditioners and some sizing considerations, and then we'll talk about heat and cooling, basically distribution systems. So forced air systems that blow conditioned air around buildings, and also hydronic or water-based systems that push hot water or steam through radiators like we have in this room. Before I get going today, I guess I just wanted to say one thing about homework policy, which is that at least what we're thinking so far is that we will not post solutions for the homeworks. Instead, we would ask you guys to come to office hours if there's anything in the homework that you don't understand. So, you know, if there's a 6-point homework and you got 4 and you're like, how did I miss the other 2 points? We would ask you to come either on Zoom or in person to office hours, either with me or with Priya Darshan, our TA, and then basically discuss. So it's perfectly fine, totally understandable and expected if you're missing points on homework. Like, that's just how homework goes. But if you want to remedy those misunderstandings, please come talk to us in person. Does that make sense? Does it sound okay? Okay, all right, great. Okay, and then just a reminder, we have our third homework due Thursday night, just before midnight Eastern this week. Okay, so outline for today, we'll talk about heating with electricity through both electric resistance, it's called joule heating, and also through heat pumps. We'll talk about air conditioning, a note on sizing, heating and cooling equipment, and then, yeah, we'll talk about some distribution systems for residential and commercial heating and cooling systems. And then we'll talk about basically some models, essentially, of fans and pumps and things like that. Okay, so the simplest kind of heating and cooling for a building, I think, is the classic heating element, which uses electric resistance. Basically, it's a hunk of metal, typically in a loop, and it's just a big resistor. And you flow current through this thing, and it gives off heat, basically. And a model of this thing is fairly simple. You have work coming in, essentially electric power as an input. The system here, this just denotes the U of metal that we see up here. And then we have an output of heat transfer. And so that's happening basically by all this metal getting very hot, and then typically either air or water being in thermal contact with that metal and then heating up. So that's what the Q denotes. So if we look at conservation of energy on that thing, at least as long as it's operating in steady state. So the metal itself will have, if you just begin, if say it's at room temperature, and then you just begin to let current flow through it, there'll be a warm-up phase where the metal itself, over the course of maybe 30 seconds or a minute, goes from kind of room temperature up to a couple hundred degrees above room temperature, Celsius typically. So, and then it'll begin to operate in kind of a steady state. So it'll stay at about the same temperature, and then the electricity going in will roughly equal the heat coming out. And so conservation of energy basically just says, again, that the electrical power going in is equal to the thermal power. By the way, first law, second law, these are thermodynamics terms. So folks who didn't take thermo in kind of a mechanical engineering concept or context, rather, that's what that means. Conservation of energy is the first law of thermodynamics. Okay, and then we can define, you could call it an efficiency or a coefficient of performance for this thing, which is basically just the heat transfer output divided by the work input, which here is electrical work. So it's just the Q, the output, divided by P, the input. And as long as the thing is operating in steady state, that's equal to 1. So it has 100% efficiency, basically. And the physical mechanism here is what's called joule heating. So probably should have put an illustration of this in here, but within this solid, atoms basically are arranged in sort of a lattice, and they have intermolecular bonds, quite strong, kind of holding them in a fairly rigid position. And then electrons flow through there, and as they're flowing through, they kind of bash into atoms that are making up that sort of ladder type structure. And that causes things to vibrate, and vibrations at the macro scale manifests at the macro scale as temperature increases, basically. So that causes the thing to heat up. Okay, and so this stuff is, it's an old technology, basically as old as people understanding how electricity works. It is dirt cheap to install and approximately lasts forever. So you can find heating elements that were installed, 80 years ago and that are still working just fine, essentially because it's just a big hunk of metal. But it's quite inefficient, at least compared to another electric heating technology called heat pumps, which we'll discuss next. So it's quite inefficient, and therefore the electricity cost to actually run the thing can be fairly high. Yep.
What do you mean by efficient there? Because in the previous iteration,
right. So what do we mean by inefficient? Here I'm saying it is perfectly efficient, right? It's a 100% efficiency. So what we'll see is that there's a metric called coefficient of performance, which is still defined in the same way, the heat transfer output divided by the network input. But for heat pumps, that's actually greater than 1. It can be, 3 or something like that. So compared to that, COP of 3, this thing is basically 1/3 as efficient. It uses 3 times the power for a given amount of heat output. Does that make sense?
Yeah.
But that's a very good question. Yeah, thank you. Okay, so what is that machine, that heat pump thing? So we'll talk about it kind of at an abstract level first, and then we'll get down to a little bit more of a kind of component level description. But basically, a heat pump is just a thing that pumps heat, it moves heat from one location to another, a colder location up to a hotter location. And it uses work, typically electrical work, in order to do that heat transfer process. So if we look at conservation of energy, again, assuming kind of steady state for the system, so its internal energy is not changing, then we get that the inputs, the heat transfer that it's absorbing from this colder region, plus the electrical work that we're putting into it from the power grid, say, is equal to the heat transfer output that's going to the hotter region. So you could think of this hotter region as like the air in this room, and the colder region could just be the air outside. And this system thing that we've drawn here could be a bunch of equipment, mechanical components and stuff like that, that through clever design basically move heat in this kind of cycle. Okay, we call Q out here the capacity of the heating system. So, if you're trying to figure out how big of a heat pump you need to keep a building cozy in the middle of winter, you'd figure out essentially what the demand for heat would be using stuff that we talked about in the last couple of lectures on buildings. So you'd maybe estimate the thermal resistance between the indoor air and the outdoor air, and then look at typical temperatures inside and outside, get an estimate of how many kilowatts thermal or how many BTUs per hour, if you're using English units, you might need. And then you'd choose a heat pump, basically the size of all the components, such that its capacity Q out is roughly equal to that number. We'll talk more about that in a minute. By the way, as always, if you have questions or comments, please let me know. Okay, so the coefficient of performance, and here I'm using the symbol eta, or eta, I guess the Greek would pronounce it, which typically denotes an efficiency. And an efficiency is typically normalized between 0 and 1. But here I'm using the same symbol to denote the same thing, the ratio of the heat transfer output to the network input. But for heat pumps, that can be greater than 1. So it's basically defined as the useful thing that we're delivering, the heat transfer output, divided by the costly thing that we're putting in. And that's the same kind of notion as efficiency. But because we have this other thing here, this kind of free heat that we're absorbing from some other scenario, some other region, that we get basically that the ratio of these two can be greater than 1. So if you take the first law, you plug it into the COP definition, you do a little bit of algebra, you get that an expression for this thing, the COP, is 1/1 minus the ratio of the input heat transfer here divided by the output heat transfer. Okay, and then from what's called the second law of thermodynamics, or the law of increase of entropy, we get what's called a performance limit here, the Carnot performance limit, named after a mechanical engineer, physicist, mathematician named, I think, Sadi Carnot, a French guy who lived maybe in the 1800s. And he showed basically through the second law of thermodynamics that this coefficient of performance for a heat pump cycle is upper bounded by the term that shows up on the right-hand side here. So it looks just like the expression for eta here, but you just take the Q's and you replace them by the temperatures at which those heat transfers are happening. So we take the cold temperature Tc and the hot temperature Th here, take the ratio and plug them in, and that gives us the Carnot limit. And by the way, to use this, both of these temperatures should be in an absolute or thermodynamic temperature scale. So in the SI system, that's Kelvin rather than Celsius. In the English system, it would be Rankine rather than Fahrenheit. Okay, so the only thing that matters, at least for that theoretical performance limit, is the ratio of the cold side temperature to the hot side temperature. And here is that thing that appeared on the right-hand side, 1/1 minus T cold divided by T hot, the Carnot limit. So you can see that as we get down to 0 in this ratio, meaning the cold side temperature is absolute 0, the efficiency goes to 1. So in that limit, basically we're not getting any heat transfer in from the cold reservoir because it's as cold as it is possible to be. And so all we're doing is taking the electric work input and just converting it to a heat output. And so we get COP of 1 in that setting. And then as we approach the limit where the cold side temperature and the hot side temperatures are equal, then the COP in theory can go to infinity. So if we look back at the equation here, if this thing is equal to 1, we get 0 in the denominator and we get infinite COP. So what this basically tells you is that if you're working between two temperatures, say the outdoor temperature and the indoor temperature, on a mild day, when the outdoor temperature is close to the indoor temperature, the COP can be quite high. But on a more extreme day, when it's really, really cold outside, and we like it nice and toasty warm inside, that temperature difference is going to be really big. The ratio here will be small, and you'll be further down here on the COP limit. So this tells you that heat pumps basically get less efficient as the outdoor temperature gets colder, at least air-to-air heat pumps. And I'll talk about what that means in a second. Okay, so this is all kind of theoretical, right? But how do these things work in practice? So this is an illustration by an artist named Nicole Kellner of something that I said on social media 7 years ago, and that got quoted in a podcast that I like called The Energy Gang. And so basically the challenge was to explain how a heat pump works to like a 4-year-old or a 5-year-old, I guess. So the idea is that a heat pump is like a gnome with a bucket running in circles. So they wring some heat out of the cold outdoor air, move inside and dump the heat out in the house, have a little snack of electricity to keep up their strength, and then basically repeat the cycle. So sort of fanciful, maybe not quite at the level of grad student brains that we have in this room.
That's from master's thesis, right?
Yeah, this was my master's thesis. Yeah, I did some serious GNOME modeling. Yeah, exactly. Okay, so then slightly more sophisticated, and I like to think, so this is an XKCD comic from about a year ago, something like that, and I like to think that that Randall Munroe, the artist who draws XKCD, listened to the podcast or saw on social media this art that Nicole drew, and then had this idea for a human-powered heat pump. But he's a pretty smart guy, so he probably just figured it out. But anyway, so we can think about how this works. So it's been a minute since I've looked at this, but let me try to understand it along with you guys. So we have the warm region is inside, we have the cold region is outside. And I think that basically red, the deeper red means hotter. And sort of the darker blue, I think, means colder. So inside we have kind of a warm house and we have kind of a cool outdoors. And so the person walks out carrying basically an accordion full of air or something, some mystery substance, right? Walks outside. Okay, so we had this kind of warmish air, walk outside. Now there's warm air inside the accordion and cool air outside. So there's going to be heat transfer basically from the accordion to the outdoor air, right? And so this thing is going to cool down. And as that happens, I think also the person there also doing some work on it at this point, basically extending the accordion so that the gas inside expands. And as that happens, it may cool down and absorb more energy from the outdoor air. Okay, so now you let some heat transfer happen. Basically, you have really cold stuff in here and only kind of cold stuff outside. So heat flows from the outdoor air into here. There's energy transfer into the accordion. Okay, it reaches equilibrium, and then they walk inside. Now we have sort of warm indoor air and cool air inside the accordion, which is not helpful, right? It's not going to get us heat transfer into the inside air. So in order to make that happen, they squish down the accordion, right? They compress whatever is inside there. You could call it a refrigerant. It might be air, it might be something else. Compress it. And in that compression process, they're doing work. So energy is flowing basically from their muscles into this accordion thing. And that transfers energy into the stuff inside there until it gets quite hot. Now they stand there for a while and do a heat exchange process where that hot stuff inside the accordion basically bleeds heat into the warm indoor air. And that's how we're providing this useful service of heating the indoors. Now the indoor is a little warmer and you repeat the cycle, walk back out the door. And that takes you back to panel 1. So this would be, it's a heat pump, and the COP of this thing would be the ratio of like however much stored chemical potential energy in the bonds and the foods that this person ate, however much of that is being transferred into the refrigerant here. So that would be the work input, and then the heat transfer output is basically what you get during this phase, the sort of heat transfer phase. Okay, and the caption here is manual heat pumps are such a pain. Obviously, this is not a thing that anybody would really do in practice, but I do think it's a nice illustration of what basically a heat pump, the machine, is trying to do. Okay, so this is at least cross-listed as a mechanical engineering class, so we can talk about the actual mechanical components that make up a real heat pump machine. And those are basically 4, at least in kind of the simplest implementation. So we have 2 what are called heat exchangers. They're just places where 2 fluids can exchange heat, kind of as the name says. We have a compressor, which basically moves a refrigerant or a coolant around in this cycle. And then we have kind of a magical component called an expansion valve, which I still don't fully understand after having taught thermodynamics a bunch of times. Okay, so what each of these things does, so basically, oh yeah, sorry, and then you could draw a dashed line around this whole thing. And if you only looked at the inputs and the outputs and you didn't think about the components on the inside, you would have the same schematic that we had when we show the kind of abstract heat pump drawing. So you'd have a work input here, a heat transfer input here from a cooler place, like maybe the outdoor air, and then a heat transfer output here, maybe to indoor air. Okay, so as the refrigerant is flowing around here, let's see. We'll start at the end of the evaporator here. So at this point, it's a cool, low pressure vapor. And I think I'm using a different coloring convention on the cool side than the XKCD artist drew. So for me, the light blue is very cold, and the dark blue is a little cold. It's cool. Anyway, so we take a vapor, which basically just means a gas, and we put it into a compressor. A compressor is like a pump, but it pumps gas rather than pumping liquid. And this thing uses work. It's a rotating machine. There's a motor in there that spins a shaft and pushes basically vapor through here. And as that happens, it pressurizes the vapor. So we go from a low pressure side to high pressure, and it raises the temperature as well. So red here indicates high temperature. That goes into this heat exchanger called a condenser, because we take vapor or gas and we basically condense it into a liquid state in that device. And then that gives a heat transfer output. So you could think of the refrigerant in here and then maybe a stream of air from a supply air duct, for example, out here. And so there'd be cool air coming in. It would do heat exchange essentially with the hot vapor in here, and it would cool down the vapor, and then the vapor would do a phase change. It would begin to condense. And as it condenses, it would give off energy in the same way that in order to boil water, you need to put in energy. It's just the opposite of that process. Okay, so then we change phase from vapor to liquid, and we reduce the temperature from hot to warm. And then we get to the magic of the expansion valve, where we take basically a high pressure liquid, we flow it through essentially like a little wiggly restriction. And on the outside, we get a very cold, low pressure liquid. And don't ask me how. Someone in this room probably knows. And I've tried to explain this in front of like 100 sophomore thermodynamics students before and just like ended up confusing myself. So not every fluid, first of all, when it flows through an expansion valve, will get colder. Some of them will get warmer. So it's a property of the material that you're working with, and it has to do with some fairly complicated fluid dynamics that I don't fully get. But anyway, this cool component basically makes warm high pressure stuff into cold low pressure stuff, at least with the appropriately chosen substance for the refrigerant. Now we have very cold low pressure liquid. We flow it through the evaporator. And the idea here is that the refrigerant is colder than the outdoor air, if that's the outdoor reservoir that we're working with. And so you might have, 5 or 10 degree Fahrenheit outdoor air, but you might have negative 20 degree Fahrenheit refrigerant right here. And so you get heat transfer from the cold outdoor air into the refrigerant. And so that basically boils the refrigerant. It converts from liquid phase to vapor phase, and it maybe warms it up a little bit as well. And then we're back to the beginning state of the cycle. So who's like, I've seen this a million times, this is super boring. Okay. And who's like, oh, this is kind of new and cool. Nobody. All right. All right. So next year I won't spend as much time on this. All right. Anyway, so this is another schematic of what and what's called an air to air or an air source heat pump looks like. So the components basically would be the compressor and one heat exchanger. The evaporator would be outside, and the other heat exchanger, the condenser, would be inside, and the expansion valve typically would be inside as well. Sometimes it may be outside. And yeah, so these things are basically a heat exchanger is a fancy way typically of saying pipes. It's just wiggly pipes with some fins on it to increase the heat transfer area. And they're using different symbols here. The W dot, that means work or typically electrical. Okay, so we talked about a sort of theoretical, nice, smooth performance curve, the Carnot performance limit. But actually, real heat pumps are nowhere near as efficient as a Carnot, a theoretical heat pump. And so typically when we're doing modeling, trying to understand, say, how much electricity a house is going to use if it's using a heat pump to stay warm, we need to typically look at some real performance data. So to do that, one nice data source is maintained by the Northeast Energy Efficiency Partnerships, or NEEP. And they collect data that basically manufacturers of heat pumps report. So this would be companies like Carrier and Mitsubishi and Lennox and Daikin and Midea and many others. So basically they make spec sheets. So when you're trying to choose between two different heat pumps, they can say, oh, here's how big it is, here's its heating capacity, and here's how efficient it is. And so you get the cost and you get the efficiency, and you can kind of compare between units and make a trade-off that works for you between the kind of initial cost up front. Typically a more efficient piece of equipment is going to cost more up front, but it'll save you money long term and stuff like that. So anyway, manufacturers publish those, and then NEEP basically rounds up all that data and puts it into a big database. And they generously make it open source. So here I took performance data from 3 different units from 3 different manufacturers. They're what's called central ducted or unitary heat pumps, and I'll show in a minute what that means. But here I'm plotting the outdoor temperature in degrees Celsius on the x-axis, and then the COP. So again, the ratio of the heat output to the electricity input for these units. And you can see that the trend that you would expect is sort of here in the data. So as it gets colder outside, the COP does decrease. We don't have as much curvature as we did in the Carnot limit. That had this kind of going to infinity thing on the right-hand side. And here it looks pretty linear. And you can see that even though the 3 different units are from 3 different manufacturers, they're all kind of roughly following a pretty similar curve. And here's, I just fit a line to that curve, and you can, or to those 3 data points rather, and here's the equation of that line. Okay, so we could take that and put it into code in MATLAB or Python or whatever, and we can run simulations that basically emulate reasonably accurately what a heat pump will do in reality. So typically, although the COP depends both on the indoor temperature and the outdoor temperature, typically indoor temperatures are kept relatively constant. Maybe you have a couple degree swing between a nighttime indoor temperature and daytime temperature, but usually it's pretty small compared to the sort of variation that a heat pump would see in outdoor temperature. So a kind of quick and dirty but reasonably accurate assumption is to basically assume away all the dependence on the indoor temperature and model the COP as a function only of the outdoor temperature. And then we fit some function, theta, typically a polynomial function, often linear, maybe quadratic. And that's a function that takes scalars as inputs and produces scalars as well. And you fit that to some data points, like, for example, the line that I showed on the previous slide. And typically the COP will bottom out at 1. Either because basically it can no longer absorb energy from the outdoor air, and it just essentially converts the work input from electricity into heat transfer output, or because they will flip to backup electric resistance heat at some point. So when the COP would drop below 1, they just switch over. Okay, so then we can look at power, electric power data and from manufacturer spec sheets, either from that NEEP database or directly from the manufacturer. And you can get a rough estimate of how much electricity a heat pump will use when it's running essentially all out. And then basically you model the capacity, and this is not the only way to model a heat pump, but it's a simple way that works relatively well. Model the capacity is just the COP times the limit of the work input. So basically the most heat that you can produce as an output is the most power you can use as an input times the COP. And then, yeah, there's this relationship between power and heat transfer. Okay, so there are many far more sophisticated ways to model heat pumps, but this is at least enough to get you started. Okay, yeah, question.
Curious, for variable speed unit, add compressor speed increasing, what does it look like in here?
Yeah, so the question is, if you have a variable speed heat pump, which rather than having a motor that's either on or off, would have one that can kind of sweep through a fairly continuous range. If you add dependence on the compressor speed to the COP, what does it look like? So there, maybe I should have included a graph of that. Maybe I could add one to this. But there, what people talk about is what's called a part load ratio and a part load performance curve. So on the x-axis, let me see if I can do this actually. Maybe not. Okay. So on the x-axis, basically you'd have the ratio of like how hard you're working to the maximum power. So you can think of it as basically just like the compressor speed on the x-axis. And then on the y-axis would be something like COP. And you'd have different curves for different outdoor temperatures, but just assuming one fixed outdoor temperature, what does one curve look like? Is typically kind of a hill shape. So the COP as a function of compressor speed typically drops off at very low compressor speeds and at very high compressor speeds. And there's kind of a sweet spot in the middle where COP is typically maximized. And actually below a certain speed for variable speed heat pumps, they typically around 30%, something like that, they will switch from modulating continuously in a variable speed fashion to actually duty cycling, so switching off and on. And that also, those kind of cycling effects can have some further efficiency losses. So you can get a pretty steep drop off in efficiency at the very low end. Does that make sense? Okay, maybe I'll prepare a slide on that and share it with you guys later. But, okay. All right, but good question, thank you. Okay, so that's kind of a quick and dirty method to simulate heat pumps. Of course, there's much more sophisticated ways. And we can also simulate the interaction between what's called a hybrid system that has both a heat pump and electric resistance backup. So the idea there is that typically, at least compared to an electric resistor, just a hunk of metal, a heat pump is pretty expensive to manufacture and to install, but it's quite efficient, so it's relatively cheap to run. Electricity costs are not too high. And then electric resistance is just the opposite. So it's dirt cheap to install, lasts forever and so forth, but it's pretty expensive to run because it's a lot less efficient. So then a hybrid system typically uses a heat pump to do most of the work. And then when its efficiency drops or when load is very high, it flips to backup electric resistance heat. So here is the mathematical way to simulate that. So on the x-axis here, we have Q, which is the heat transfer output. Or you can think of this as the thermal load of the building, how much heat is needed to keep a building comfortable. And then here P max, so this is the upper limit on electric power input. And eta here is the COP. So you can see that when Q is exactly equal to eta times P max, that means that the heat pump will be running essentially at its maximum capacity. And then the slope here is 1 over eta. So if eta is 3, the slope here is about 1/3, something like that. And then out here, the slope is 1. This is the efficiency basically of, at least in steady state, the efficiency of an electric resistance heating element. And so you might have a lot of capacity. Again, these things are dirt cheap. You could throw a bunch of them into the house. In our test house, I think we have our heat pump. Its max capacity is around 4 kilowatts. This is for a typical maybe 2,000 square foot home. And then we have maybe 20 kilowatts of electric resistance out here. So again, because it's cheap, why not? Okay, so then you can use this formula here basically, which essentially takes the maximum of this line, the line with the slope 1 over eta, and this line, the line with the slope 1. So if you take the maximum of those two, you get the thick black curve. Okay, so much for heating. So let's talk about air conditioning. So air conditioners basically are just one-way heat pumps. So most heat pumps can run in reverse and you know, just basically take heat from inside and move it outside in order to provide cooling. Air conditioners are basically heat pumps that run only in one direction. So for that reason, a heat pump typically has a significantly lower upfront cost than putting in a heating system, like say a natural gas furnace or a boiler, and also a one-way air conditioner. So in the US, something like 90% of new houses that are built have air conditioning. So basically almost every new home that gets built has one of these devices that can operate in one direction. So, why not basically allow them to run in the reverse direction as well, and then every house basically would get built with a heat pump. Okay, so there's some vocabulary terms that basically relates sort of the source of heat, and then the sink of heat, the place where you're moving heat to, and then we have vocabulary for what those devices are. And part of like working in the HVAC industry is basically just knowing all these terms. So if we have a heat pump, and in my mind, everything is a heat pump, right? But more formally in a thermodynamics class, you would say a refrigeration cycle is one, the purpose of which is to absorb heat from a colder place and move it to a hotter place. So a fridge, for example, would absorb heat from inside the refrigerator, from the air inside your fridge, and then it would move it into the kitchen. So if you pull your refrigerator out from the wall and you feel the back of it while it's running, so you can hear the compressor click on, it starts to whir, and you put your hand in the back, there's some coils, a heat exchanger, and it'll be warm. And that warmth is basically energy that's being absorbed from inside the fridge and moved out into the kitchen. A freezer as well, same thing. And then, an air source heat pump uses the outdoor air as the source of energy and moves it to the indoor air. So we call that an air source or an air-to-air heat pump. And then if you run an air source heat pump backwards, you get an air conditioner. So you absorb heat from the indoor air and move to the outdoor air. Okay, if the outdoor thing that you're absorbing energy from is the ground, so your heat exchanger, again, just pipes with fins on them, basically. If that stuff is buried, say 10 feet underground, then you'd be absorbing energy from the dirt and stuff rather than from the outdoor air. And you call that a ground source heat pump or a geothermal heat pump. And the idea there is that even on a really cold day, when it's maybe -10 Fahrenheit outside, 10 feet underground, it might be 45 or 50 Fahrenheit. So we saw that the efficiency of a heat pump depends basically on the temperature difference between inside and outside. And so if your outside temperature source is at 50 Fahrenheit rather than -10, you can imagine that your COP is going to be a lot higher. And so these ground source or geothermal heat pumps might hit a COP even on a really cold day of like 4 or 5, whereas an air source heat pump might be at like 2, 2.5. However, that improvement of efficiency comes at an increased capital cost, because to install a geothermal heat pump, you basically have to dig up your backyard and put a bunch of pipe down. Okay, so some more vocab here. So if you're absorbing energy from the outdoor air and moving it to water inside, we generally call that a heat pump water heater, or an air to water heat pump as another term. And then if you're going from indoor air to indoor water, so sometimes these things called heat pump water heaters will basically absorb energy, say from the air around them in the basement, which is itself conditioned potentially by another heat pump. And then they'll move that heat into the water. So. And then if you are absorbing energy from indoor water, so you're trying to cool water down inside and moving it outside, we call that a chiller. And all the air conditioning essentially for most Purdue buildings is provided by about 20-ish gigantic chillers that cool water down to about 45 degrees Fahrenheit and then pipe it all around campus. And then we have heat exchangers and stuff in buildings that essentially use that to absorb heat from inside. And then, okay, so if you're using the outdoor water as the heat reservoir and then moving heat into the indoor air, we call that a water source heat pump. So it's similar to a ground source heat pump. On a cold day, if you're, say, on the side of a big lake, if you go down maybe, 100 meters or something like that on a deep lake, you might find that the water temperature down there, even on the bitter coldest day of winter, is like 40 Fahrenheit, something like that. So you can use that as your heat source and basically improve efficiency relative to an air source heat pump. Okay, and there are more terms, right? But this covers most things. Most configurations you can imagine, like, I don't know, what if I had lava outside and I don't know, something else, right? So, you can come up with a lava source heat pump. Okay, so refrigeration cycles, again, are basically just heat pump cycles that run in reverse. So here, again, the idea is that we absorb energy from a cold reservoir, move it to a hot reservoir. But now the point of the thing is basically to absorb this heat Qn. And so we can run our conservation of energy again. The coefficient of performance, again, is always defined as basically the useful thing that the machine is doing divided by the costly thing that we have to put into it. So in this case, the useful thing is the heat transfer input, the Qn, and the costly thing is this P. And you do some algebra and you get something that looks quite similar to the COP of a heat pump, except there we had 1 in the numerator, and here we have this ratio of heat transfers. And we get a Carnot performance limit again that comes from the second law of thermodynamics. And there, basically, you just take all the heat transfer ratios and you turn them into temperature ratios, again, in Kelvin. And so we get another curve here. And again, it's a function only of the temperature ratio between the cold side and the hot side temperatures. And again, as that ratio goes to infinity, meaning the sort of fridge is almost at the exact same temperature as the kitchen, we can get essentially infinite coefficient of performance. And then in the other extremis, we go down to absolute zero. Well, it's very hard to cool stuff down. That's really, really close to absolute zero. And it's another law of thermodynamics, basically I think it's the third law, that says that the closer you get to absolute zero on the cold side, the harder and harder it is to cool something down further. And essentially the work you need to put in goes to infinity, and that's why the COP goes to zero at the moment. Okay, so just like with the heat pump side, we can fit a performance curve or a COP curve to performance data here. So again, outdoor temperature on the x-axis. So indoors, maybe we'd be at 23, 25 Celsius, something like that. So the delta T between inside and outside might only be kind of in the range of 5 to 10 degrees at the low end here. And so we get COPs that are significantly higher than what we saw on the heat pumps. So we can get up to COP 6 or something like that. And then as it gets hotter and hotter outside, the COP drops off. Maybe we end up at COP 3 or something when it's over 100 Fahrenheit outside. And that same organization, NEAP, they also, their data, the same database basically has both cooling and heating data for heat pumps. Okay, so one thing that air conditioners do that heat pumps don't is control humidity. So let's see, that's actually why we call an air conditioner not just a cooler. We call it an air conditioner because it also conditions the air, meaning removes or moisture from the air. So the way that typically happens is your heat exchange coil has very cold refrigerant running through it. When warm, humid air runs over something cold, just like a glass on a hot summer day, you get condensation on the outside. And so that coil basically absorbs moisture from the humid air, and then that typically pours off into some pan and then is piped outside or down a drain. So as an air conditioner is working, it'll both reduce the temperature of the indoor air, and we call that sensible cooling or sensible load. And it'll condense water out of the air, and we call that latent cooling or latent load. And so the total load is just the sum of those two. It's what you're getting from, or the amount of energy that you need for temperature change, plus the amount of energy you need for a phase change of the moisture, basically, the water. And then the sensible heat ratio, which we denote S, is just the ratio of the sensible load to this total load here. So if S is equal to 1, that means you're not doing any dehumidification. If S is equal to 0, that means all you're doing is wringing moisture out of the air. You're not cooling it at all. Okay, so often when we run simulations, like if we use the type of RC models that we talked about the last couple of lectures, all we're really talking about there is temperature changes. So all a simulation like that will provide is Q, the sensible load. So if in addition to making up for energy that's transferring through the walls or whatever, if in addition to that we're also doing some dehumidification, then we want to take basically the total heat transfer and divide that by our COP, or equivalently take the sensible load and then divide it by our sensible heat ratio. So S is typically less than 1, which means that Q total will be greater than Q. So we take that whole thing and then divide it by the COP. And that gives us basically the relationship between the heat transfer that comes out of our RC model and the electric power that would be consumed by an air conditioner. Okay, so then the important thing here is this sensible heat ratio S. And in reality, this is a very complicated thing. It depends on a lot of stuff. It depends on the weather. It depends on how humid or moist it is inside the building as well. So outdoor humidity, indoor humidity. It depends on the coil temperature. You can imagine a really cold coil might condense more moisture out of the air, and other things as well. So what occupants are doing inside the house influences how humid the air that goes back to the air conditioner is. So if I take a long, hot, steamy shower in the middle of summer, then I add a bunch of water to the air, basically, that has to be removed. And so this thing S is going to be time dependent and it's going to be kind of random and so on. But as a first cut for simulation purposes, you can set S somewhere in the range of 70 to 95%, typically, where the 70 might correspond to a pretty muggy climate like Georgia or Louisiana, and 95, that might correspond to a climate like Arizona, very dry climate. And you can also find estimates of S on the same manufacturer spec sheets that go to the performance, the efficiency data as well. Okay, so that's heating and air conditioning. Let's talk a little bit about how we size equipment for heating and cooling. So this stuff is based significantly on kind of the RC modeling, thermal circuit modeling that we did last week. So the basic idea is somehow we estimate the overall thermal resistance R between the indoor air and the outdoor air. So one way to do that is to kind of do what we talked about, I guess, in part 1 of the buildings lecture, where you think about how big the building is, what's its surface area, how much of it is walls versus windows, how good is the insulation, and all that kind of stuff. And then you sort of use rules of thumb and best guesses and kind of engineering, intuition and stuff like that, and you come up with some guess. And usually it's decent, but not great, basically. Another way to do that is to look at energy data and weather data. And this is what your homework problem number 2 is about this week. And basically use that usage data and the real climate data from the area and the house that you're looking at, or the building. And then do something like take the ratio between a temperature difference between the inside and the outside and an energy usage. And then you get basically the thermal resistance. And so without giving too much away, you should get something like that, a relationship like that in your homework this week. Okay, so we estimate R somehow, either by data or by just kind of looking at geometry and physical properties. Then we get what's called the design outdoor temperature. So this is typically not the absolute coldest it could possibly get, but it's typically kind of in like the 99th percentile of the coldest hours of the year. And ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers, they publish sheets with these design temperatures for basically every county in the US. Okay, so we get that from basically an ASHRAE sheet. We set a design indoor temperature, and that's typically whatever occupants like it to be inside the building. So for heating, it might be kind of in the 68 to 72, 73 Fahrenheit range. For cooling, it might be warmer, 75 to 80, something like that. But the idea is that you can tailor this to the actual occupants that you're working with. And then you pick some plausible value for the exogenous thermal power. So this is what you're getting from sort of everything that's not heating and cooling equipment. So this is what you're getting from the sun, potentially, from body heat, from electronics, from lights, all that stuff. And you want to pick that for heating design. You want to pick it sort of to roughly correspond to the coldest hours and times of day, which are typically in the very early morning, so around 4 a.m. So that's kind of nice because you can forget about sunlight. Sun's not going to be up at 4 a.m. in the middle of winter. You can forget about most things, actually. So you're just going to have, the fridge running potentially, and maybe some networking equipment, and then, 100 watts per person, basically, from body heat. So you can estimate this, or you can even set it to 0. It usually is not too sensitive to that. And then basically we take our RC thermal circuit model, or 1R, 1C model, and we assume steady state. So we take the temperature derivative and set that equal to 0. And then we solve for Q and divide through by eta, and that basically gives us P, the electric power input that would be required in order to meet the heating demand kind of in those design hours. So you can see that's proportional to the temperature difference between inside and outside. It has the thermal resistance, basically the insulation in the denominator here. So better insulated building is going to lead to this term being smaller, and therefore needing a smaller piece of equipment to provide heating. And then if you have more kind of heat gain inside, so more bodies, more lights, more computers, more all that kind of stuff, then this will be bigger. And again, we will decrease this. And then if your equipment is more efficient, basically its electric capacity can be lower. That makes sense. And then this thing in the numerator here, R, I'm calling the oversize ratio. And what this actually is in practice varies wildly. I once had an apartment that was it's called a FROG, freezing room over a garage, is like an acronym that people have for these things in the heating and cooling industry. I didn't know it at the time, but I was living in a FROG. They also call them in-law apartments, right? It's like a little unit that was built kind of behind the house on top of a garage. It was a lovely little apartment, secluded, very nice, private, etc., but just terribly insulated. And anyway, also very small. So I think the smallest piece of equipment they could get was a factor of 7 larger than the design heating load that I measured in that house. So here R, rather than being 1.2, was 7. But and that's actually not uncommon. So installers who put equipment in for a number of reasons are often inclined to oversize more than necessary, and sometimes much more than necessary. And so part of that, sort of cynically, is that, you know, if they can sell you a bigger piece of equipment, they make a little bit more money. But less cynically, also, you know, their business model is basically they want to come in, install some machine, and move on to the next customer. And after that transaction, they don't really want to hear from you. But if you're unhappy with what they put in, oh, it's not keeping my house warm, then you'll call them back. And those, what they call callbacks, are basically they're terrible in the HVAC installer industry, I guess. They hate them. So to avoid callbacks, they say, you know, we're going to put something in that's big, so you're not going to get cold, essentially. But anyway, if you look at the recommendations from a group like ASHRAE or AHRI, the American Heating and Refrigeration Institute, for a number of reasons, they recommend actually not oversizing crazily. So you want to be pretty close, actually, to the design load. Okay, and then sizing for cooling, very similar. It's just like for heating, but now we take into account the sensible heat ratio, and also we flip basically the sign over here. So we have the outdoor temperature minus the indoor temperature rather than the reverse, and we're adding the exogenous power. And here, this QE should actually have, you know, maybe pretty significant effect from the sun in it. Because, you know, typically the hottest hours of the year are in the late afternoon, something like 3, 4, 5 p.m. And there you can still have significant sunlight, especially through kind of west-facing windows. Okay, so then I made this point early on that heat pumps are kind of cool because they can do both heating and cooling. So rather than installing a central air conditioner plus a furnace, you can just put in one machine and have it do both, and potentially save, you know, a few $1,000s on the install. But now you get into a more challenging design problem, because you want a piece of equipment that both works for heating and for cooling. And if you're in somewhere like, I don't know, northern Minnesota, the heating demand might be, you know, way bigger than the cooling demand. So if you put in something that's sized for cooling, you're not going to be able to keep up in winter. If you put in something that's sized for heating, it's going to be like gigantically oversized in summer. And that can have some performance issues. Anyway, so there's a few ways to do this sizing. So basically, to start, you want to do the sizing calculations both for heating and for cooling. So that's the same process I just outlined. And then if basically your heating demand is less than your cooling demand, you pretty much just size for cooling. And yeah. Now, if your heating demand is greater than your cooling demand, then you've got a few options. So one is you just get a gigantic heat pump. You just size it for heating. And then you just accept, like, I'm going to be way oversized for cooling. And why that matters, it's a little bit subtle, but let me see if I can briefly explain it. So if you have a huge air conditioner serving a small thermal load, it basically will turn on when it gets hot inside the house. We talked about thermostatic control last week, right? So it'll turn on, you know, when the temperature drops below some limit, rises above some limit, it turns on, and then it'll really, really quickly cool the house down. So within a matter of minutes, boom, you've dropped from, say, whatever it is, 80 down to 76, and then it turns off. So it's doing this turn on, turn off thing very frequently, right? What you would like is for it to run kind of smoothly and steadily for longer periods. Part of that is just because, like, every time you have to spin up rotating machinery, you have to kind of overcome inertia and friction and stuff like that. And so there's some energy penalty to doing that. So if you're doing it more and more often, then you get less and less efficient. There's also a humidification issue, which is that if you are short cycling, you only run for a couple of minutes, and then maybe you don't absorb much moisture from the indoor air. The coil maybe doesn't get as cold as you would like it to, so you don't get as much water condensing out. And so then humidity can rise. Also, you know, there are other more technical reasons based on how fans and things like that are controlled, but basically humidity performance can get worse if you have very oversized machinery. Okay, anyway, so that's why you might not want to do number one. You could do number two, which is basically size for cooling. Just get an appropriately sized thing for your air conditioning load, and then add backup heat, which could be, a number of options. And then sometimes you, like again, for northern Minnesota, you might find that you just can't find a heat pump. You can't do the second option here. Sorry, the first option here. You can't find a machine that's big enough to meet all of your heat demand on the coldest hours of the coldest night. And so there you basically buy the biggest thing you can, and then you add backup heat again. So any ideas of what backup heat could look like? So suppose you're putting a heat pump into a house and, for your in-laws or something, or I don't know, your grandparents in northern Minnesota, and it's not going to be big enough for them, and you want something else to keep them cozy. So what else could you put in as a heat source? Blankets. Yeah, just here's a heat pump, grandma, and here's a whole bunch of blankets for you for this winter. Yeah, maybe it could be blankets. Anything else? Yeah, you could put in a radiator, and there the fuel source wouldn't be electricity. Probably it might be, propane or heating oil or natural gas. Yeah.
Improve insulation.
That's a good idea too, right? Like if you can't get a heat pump that's big enough, maybe that means that the house is badly insulated and you need new windows, or you want to put some insulation in the walls, something like that. It's a good idea. Yep. Yeah, auxiliary heat. We talked about how you can put in electric resistance alongside a heat pump. And so it won't be as efficient, but if you're not using it, too many times per year, then maybe that's okay. Yeah, so there are lots of options. You could put in another heat pump. So there are basically central heat pumps, and there are what are called point source heat pumps or mini split heat pumps. We'll show a picture in a sec. But the idea is, you could put in a little heat pump basically just in the rooms where people hang out at the time when your big heat pump won't be able to keep up with demand. So you put one in the bedroom or something, keep it cozy overnight. Resistance or auxiliary heat, a heating element, we talked about that. Thermal storage is another option. So you could put in something like a big hot water tank that you could charge during the day, possibly using maybe solar power if you have solar panels in the house. And then you could basically use some of that hot water to provide backup heat. Wood, so fireplaces, wood burning stoves, things like that are often very cozy and kind of nice options. And then there's propane, heating oil, and natural gas as well are also common options. Question?
You could also use the heat storage if you were in a situation where your air conditioner was oversized. Do the first.
That's a good point. Yeah. So the comment is you could also use heat storage for cooling, basically, in the situation where your air conditioner was way oversized. Yeah, that's a good point. And we'll talk about thermal storage, I think, next lecture. But just as a quick preview, there are some types of thermal storage that you can use both for heating and for cooling, and other types that you can't. But that's one advantage of, for example, like water as a storage medium, is you can make it hot and use it for heating. You can make it cold, and it's cold enough before it freezes. Basically, you can use it for cooling as well. Yep, very good point. And actually, designing and sizing thermal storage, that is a pretty cool problem. And there's been a lot of work on it, but there's still a lot of work to do for R&D purposes. And so that could be a nice class project. Aaron, for example, is working on that for his PhD thesis and may do a project on it this semester. So if that's interesting to you, you could think about teaming up with Aaron. Okay, so just one quick example of sizing for, let's say, a house in Lafayette, this kind of area here where Purdue is. So our design outdoor temperature for heating is -16 Fahrenheit, Celsius, which to convert to Fahrenheit, you roughly double it and then add 30. So it's a bit above 0 Fahrenheit. And then I'm just picking kind of arbitrarily a design indoor temperature of 21 Celsius. So it's kind of low 70s, 72, something like that Fahrenheit. And then for the exogenous thermal power, I'm saying we're getting 1 kilowatt kind of for free overnight in the coldest hours. And that's, again, just, the router, a computer idling, the fridge, stuff like that. And then the COP in those coldest hours, I'm using 1.8, which is reasonable for what's called a cold climate heat pump, something that's designed to work well even in very cold weather. And not all heat pumps are designed to do that. So you need to be a little careful if you're recommending those to friends and family. And then on the cooling side, 32 for the outdoor temperature, which is around, I guess, 100 Fahrenheit or high 90s. And then a little bit warmer for the thermostat setting inside. So this is maybe 77, something like that Fahrenheit. And then more energy gained from basically the sun through windows and stuff. And then the air conditioner COP is typically, even in pretty hot weather, it's typically pretty high. So for a good unit might have a COP of about 4. Sorry, COP is coefficient of performance. I don't know if I said that. And then the input parameters that I'm using here is R of about 3. And then oversize ratio, little r of 1.3. So basically 30% oversized relative to design load. And then I'm using a sensible heat ratio of 0.8. So 80% of the air conditioning we're doing is cooling the air. And then 20% is dehumidifying, basically. So if you take these numbers and you run them through the formulas that I showed a couple slides ago, you get a capacity for heating of 8.2 kilowatts and for cooling of 2.7 kilowatts. So it's like a factor of 3 difference. And that's owing to both the fact that, it gets colder basically in Lafayette when it goes hot, and the COP is typically better for cooling than for heat. So the biggest air-to-air residential heat pump that I could find in that NEEP database has a rated capacity here of about 7.5 kW electric, which is not big enough to meet all of the demand for this kind of typical house in this area. So we need some kind of backup heat. And the idea there typically is what people do is they just put in electric resistance because it's cheap. Okay. And by the way, this is the configuration that we have in our test house just off campus. So we'll do a tour of that and you can see some of this stuff for yourself. Okay, so let me get into a couple of configurations for common sort of distribution systems. So maybe the most common, certainly the most common in this area is a central ducted system where you have typically what's called a unitary air conditioner or heat pump. I think in this illustration, this is for cooling operation. But unitary, I think, just means that they're like packaged chunks of plastic and metal that you can like buy as a unit. There's an indoor unit and there's an outdoor unit. That's where I think unitary comes from. But the idea here is that you have the compressor and one heat exchanger outside. You have the other heat exchanger inside and a fan, also called a blower for some reason. HVAC vocabulary, I don't know. So how this works basically is you have, let's see, outdoor air that's fairly maybe relatively cool. It might be 80 degrees Fahrenheit, something like that. Goes into a heat exchanger where there's pretty hot refrigerant, and then comes out at maybe 90 or 100 degrees Fahrenheit. And that is both going to cool down and also condense the refrigerant out here. Then it goes through basically piped inside and through the expansion valve, gets very cold. And then in here, in this heat exchanger, you'd have super cold refrigerant. And then this fan or blower is basically moving air over that to cool down and dehumidify the indoor air. That goes up into supply ducts. Oh, sorry. Yeah, a little hard to see, but the blue here is supply ducts. So these might come out in the top. Often in this climate, I think, I don't know, in my house at least, these are called registers, the basically vent things where the hot or cold air comes out of. In my house, they're actually at the floor, but I don't know, sometimes they're up high. You can imagine for cooling operation in a cooling dominated climate, you'd want the supply registers high because cold air would come up and then kind of float down and you'd have nice, comfortable mixed air. Rather than if they were at ground level, you probably just get like a layer of cold air sitting at the ground. So then you might want to put in a fan to do some mixing and stuff. Anyway, so cool air comes in here, then it sort of falls down, mixes and cools the space. And then the air goes into return air ducts, either in the floor, sometimes again on the wall. And then the fan basically sucks that air down into the basement. And that cycle repeats. Questions about that? Okay, so that's a central ducted system. Also, I mentioned these are called, there's sort of point source heat pumps or what are called ductless mini split heat pumps. Mini means they're kind of small, duct means there's no duct, or ductless is no duct. And then split means there's, again, both an indoor and an outdoor unit. And so the idea here is that you, run the cycle as well. And there's this conduit here, this kind of plastic pipe thing, has refrigerant lines in it, 2 of them, both a supply and a return line. And those come inside the house. And then this is the indoor unit. And there's a little fan in here that basically just sucks, warmish air maybe from the ceiling and then blows coolish air down, something like that. And so these were not common, these ductless mini splits in the United States, and they still aren't really. But a lot of the sales of new heat pumps that you see are actually this configuration. Part of it is that they're kind of more modular and a little bit cheaper maybe to install and to manufacture. But also you can put them in kind of as supplements. If you have a part of the house that just gets really cold and it's not feasible to go in and insulate the heck out of it, you could put a little heat pump out there, basically, think of a 3-season room or something like that to keep it cozy. Yeah, question.
Curious, why do they tend to put these next to doorways? Wouldn't you expect that to be like the highest heat pump location in the house?
Yeah, so why do they put these things next to doorways? I actually don't know if they do. They may. This is maybe a bad illustration because you make a good point that like if it's the middle of winter and you're trying to do heating here, you're getting all this really cold air basically flowing through here. So maybe that hurts the system performance. Yeah, that's probably right. And I think, again, the placement of these things is kind of like the placement of the supply registers in a central ducted system. For heating operation, you might want this thing closer to the floor so that you get warm air and then it kind of rises and mixes. But for cooling, you want it near the ceiling. And so there's some trade-off there and so on. Anyway, just kind of showing configurations here. So some houses in the US, I think it's maybe around a third of single family homes in the US have what are called hydronic or water-based distribution systems. So here, rather than blowing air around, you pump water around. So here again, we have an outdoor unit. So it's a little hard to see, but this thing here, labeled number 2, would be the compressor, and then one of the heat exchangers for the heat pump cycle. And then it would either, depending on the configuration, it would either send refrigerant or water. Or potentially some sort of water and like glycol mixture or something like that to keep it from freezing. But it would pump that inside. And then that would go through radiators where you'd have, hot water or steam coming into the radiator and then cooler water coming back after, cooler air from inside wafts over the radiator and absorbs a bunch of energy. They can also do water heating. So you might have hot water also piped not only to radiators, but also to a hot water tank. So you might have one heat pump basically that provides both domestic hot water and space heating. And then typically you draw, again, this might be like a mixture. It could be refrigerant, it could be a water glycol or something like that mixture. And then you'd have in here something more like potable water, and that would come out and go to showers and stuff. And then typically the wastewater from showers and faucets is piped down into the sewer. So although it still has a lot of heat content in it, it's usually not recaptured because it's dirty. And then you could have something like underfloor heating. This is not common in the US. Usually we have radiators in hydronic systems, but in more modern buildings, especially in Europe, you can find what's called radiant heating or radiant slab heating or thermally active building systems. Tabs is another word for it, where you have basically a hunk of concrete and inside of it you have a heat exchanger, and then you can pump water, hot water or cold water through that thing. And it provides kind of a cozier feel of heat often, and sometimes more efficient. Okay, and then in commercial buildings, typically they have what are called variable air volume systems. Not all systems will have these, but more newer buildings typically do. But the idea here is you have what's called an air handling unit or an AHU. And this is typically a big thing that'll sit like on the roof. So if you ever see a shot from a helicopter or an airplane of something like a Walmart, they will just have like a million of these what are called RTUs, rooftop units, sitting on top of the thing. But basically air handlers that are providing supply air down into the building. So this blue thing here, this is a duct. So unlike the residential systems, which typically do not have any fresh air intake, so in most houses, ventilation is done kind of passively through leaks basically around the framing of doors and windows and stuff like that. But in commercial system or buildings, which may be much bigger and they might have like core zones that just don't have any exposure to the outdoors, you typically need some sort of mechanical ventilation. And that's usually done by mixing in outdoor air with the return air that comes back from a space. Then that gets filtered. Again, the outdoor air could have stuff in it, and so could the return air. So there's a filter, it goes over a cooling coil where it might both get dehumidified and cooled. And then there's a fan that blows that. VFD stands for variable frequency drive. And this is basically, a continuously modulating motor controller thing. So you can ramp up or ramp down the speed of the supply fan kind of smoothly. And then you get air maybe at around 55 Fahrenheit, and it's blown to a bunch of different zones. So there's kind of a uniform temperature of supply air that gets blown all around the building. And then different zones might need different amounts of heat, or some of them might even need cooling while others need heating. And so they have typically what are called VAV boxes here. And I'll show you the internals of that on the next slide. But that will do further maybe conditioning of the air so they could heat it up a little bit further if needed, and then put supply air into the room. And typically these systems, so I think we have one in here. You can see that there are 2 supply registers in the ceiling. So above those, there may be, depending, I don't know, this is an old building, so maybe not, but there may be boxes like this up there. And then typically heating in these VAV systems is done hydronically. So you can see that we have radiators in this room where hot water or steam is being pushed through them. Okay, so that's roughly what a VAV system looks like. And then you'd have a lot of copies basically of this thing here at the other zones. And they'd all kind of have their own VAV boxes and stuff. And then the return air would mix. It's not really shown here, but you'd have return air coming from a bunch of different zones. It would all mix in here. And then we'd blend in outdoor air and kind of repeat the process. So here's what's inside that VAV box. So this is this component right here. We're zooming in on that. So it takes in basically supply air from that shared supply air duct. It may be something like 55 Fahrenheit. And then it basically has a damper with a little motor on it that can open or close depending on how much flow is needed in the space. It's got a controller there. And then typically they will have a what's called a reheat coil as well. And so this is, again, just a heat exchanger, a bunch of pipes with fins on them, and a valve here that again has another motor on it that can control what's called the valve position, how far open or closed that valve is. And that's basically just like, turning on or off a faucet. So it controls how much water, hot water flows through this reheat coil. And sometimes the buildings will have electric resistance here instead of hot water, but usually you can get more efficiency with a water system. And so then you may reheat the air a little bit and then blow it into the space. Oh, and this is called a diffuser or sometimes a register. That's about it. So not a lot happening inside of here, but you have control basically over both flow and temperature from these 2 devices and the control system. Okay, so wrapping up here, any questions about these kind of system configurations? Okay, so just to reiterate, there's a wide variety of configurations of both, the equipment that supplies heat and also the distribution system that moves it around. And I haven't shown you all of them here, obviously, but I've just shown you kind of a few of the most common systems in both residential and in commercial spaces. All right, so suppose that you're doing some project where you want to use, I don't know, fans or pumps or heat pumps or chillers or whatever it is in some HVAC system. You want to use them to provide some services to the power grid, or you want to control them more efficiently, reduce emissions, reduce energy costs, something like that. So it can be handy then to be able to model the components that come into those systems. So here is a model of heat transfer in a forced air heating system. So this would be, something like basically where air is the energy carrier. So this would be that central ducted residential. It would be the VAV system on the cooling side, at least with the air. And it would be the mini split system as well. So here you'd have a building, you have air coming in at some mass flow rate. So M dot just means the kilogram per second mass flow rate of the supply air coming into the building. And then you have, again, mass that typically, if you have a balanced system, you'd have the same mass flow rate coming out. And then the return temperature, T-ret here, is usually about equal to the temperature of the building and the space itself. The idea is that, if we have air coming in from these supply diffusers, that it would mix before getting sucked out of a return. And so therefore, it's about the temperature of the space. And then you have heat supply coming in RC type model. This would be the solar heat and the body heat and stuff like that. And then you have conductive losses basically going out through the building envelope. So this is our delta T divided by R term. So if we do a first law energy balance on this system, the inputs are going to be equal to the outputs, basically, up to maybe changing the temperature of the indoor space, and that's what shows up on the left-hand side here. So this looks like our 1R, 1C thermal circuit model, but with our QC term equal to basically an m dot, the mass flow rate, times Cp, the specific heat of air at constant pressure, which tells you for a given mass of air, or per unit mass of air, if you do a 1 degree increase of the energy, how much, of the temperature, how much energy is stored in the air. And then we have a delta T between the supply side and the return side, which again is about equal to the temperature of the space. And then we have our exogenous term over here as well. So questions about that? Okay. So anyway, this m dot C delta T thing shows up all the time in HVAC engineering. It's usually the way that we estimate things like heat transfer for cooling or for heating, is we look at flows and we look at temperature differences, multiply them and throw a specific heat in there and you get energy, basically. And then hydronic or water-based heat transfer looks very similar. Again, you have the same kind of inputs and outputs to the RC model, but now we'd have a supply water temperature and then a return water temperature, which in general won't be equal to the space temperature. So, we might have steam flowing into that radiator at over 212 Fahrenheit or something, and maybe it comes out at 190 Fahrenheit. So it's still far hotter than what we have in the room. So if we do the power balance again, we get a very similar looking term, but now rather than having a T supply minus T, we have T supply minus T return. And then here C is the specific heat of water. And water is pretty well modeled as what's called an incompressible substance. So we don't have two different specific heats, one for heat transfer at constant pressure and another one for heat transfer at constant volume. We just have one. And so there's no subscript, we just call it C. And that's 4.2 for water. Okay, so again, that m dot C delta T calculation. And then fans and pumps you can model in a couple of different ways. And I'll offer in the next 2 slides 2 of those ways. They're both very simplified, but they can be good enough for kind of a first cut simulation or maybe for control design. So here we have the device, the fan or the pump, and this thing has a motor and it has some shaft and it has blades or whatever. And we have electric power going into it. We have a mass flow coming in and another mass flow going out. And I'm assuming that those are balanced, so we're not accumulating basically air or water inside the thing. And potentially the temperature of the fluid is changing and maybe the pressure of the fluid may be changing as well. So for a fan, we have the power basically coming in is equal to m dot, again, times Cp times the delta T here. And this is using what's called an ideal gas model of air. For those who are better at thermo than me, you'd know that this is really, we want an enthalpy change. So we'd have an m dot delta H rather than a Cp delta T, but in an ideal gas model of air, which is pretty good under the kind of standard temperature and pressure conditions that we work with in HVAC systems. We get that the enthalpy is just basically, or the delta of the enthalpy is just C times the delta T. So that's for a fan. For a pump, we may be dealing with pressure changes as well. So you can think of a pump, maybe in located some low elevation near some reservoir for a municipal water pumping system, say, and then it might push fluid up a big hill. And so it would be basically dealing with a pressure change in the fluid as well as potentially a temperature change. And so this is using, again, what's called the incompressible substance model for water, but that basically says that a change in enthalpy is equal to C times the temperature change plus the pressure change divided by the density. And this notation here is admittedly terrible. So I have 3 things that all look like P's in this one equation. So we have rho, which is not a P. This is the Greek letter rho, which is the density of water. We have capital P, which is the pressure at the inlet and the outlet side of the pump. And then we have on the left-hand side, little p, which is the electric power input to the pump. And you can convince yourself if you work the units here that a pressure difference divided by a density is going to have units essentially of energy divided by mass. And so when you multiply that by units of mass per time, you get units of energy per time or power. Okay, so that's one way to model pumps and fans. Another way is to use what are called the pump and fan affinity laws. And there are a bunch of these, but the one that's relevant for us for simulation purposes basically says that the work input is going to be proportional to the cube of the mass flow. And this constant of proportionality, alpha here, is just the ratio of the power under rated conditions divided by the mass flow under rated conditions. So for a residential fan, for example, you might say, look at a spec sheet from a manufacturer and say, this fan is rated for 1200 CFM, cubic feet per minute. And at that rated flow, it uses 700 watts. And then you take the ratio of those two, the 700 watts divided by the CFM, which is a volumetric flow rate, that's a V dot, multiply it by density to convert it to an M dot, and then do a bunch of unit conversions. And then that would give you this alpha here. And this cubic affinity law works both for fans and for pumps. But in reality, this theoretical relationship usually doesn't hold all that closely. So typically what people do instead, at least if they have access to real performance data, flow measurements and power measurements, is they'll fit to like a curve fit typically a polynomial model that says that the power is some polynomial function of the flow. And here we're using a cubic, so it would basically have this term in it, but it would also have a quadratic, a linear, and a constant term. Okay, so that is all for today. I'm a minute over time, but I guess if folks have questions for a minute or two, so feel free to leave if you want. If you have questions, also feel free to hang out and ask for a minute or two. Yes.
Like the residential models are, do they typically follow like one of these schemes, or are they often mixed?
Okay, so the question is, for the residential distribution systems that I showed, do they typically follow only one of these schemes, or can they be mixed? Often they're mixed. So an older house that doesn't have air conditioning may only have one. So it might only have radiators, but no AC, for example. But commonly when people do renovations of buildings, they'll say, yeah, I'd really like air conditioning up on the second story. It gets really hot overnight. And so they might put a mini split heat pump up on the second story. Then you'd have both. Or you might have a central air conditioner, which would operate with this ducted system, and then a hydronic heating system, a boiler and radiators for heat. Okay, sorry, let me stop there. Thank you guys all, and I'll see you on Thursday.